herzlichen Dank, Willi Sohn, für diesen wunderbar bereichernden Vortrag über das Wundermittel CO2. Es wird nun gefolgt von dem Vortrag von Prof.Dr. William Happer aus den Vereinigten Staaten, ob denn Wasser durch CO2 überhaupt versauert. Ich begrüße ihn herzlich auf die Bühne, Prof. Dr. William Happer.
Okay, well, first I'd like to thank the organizers of this conference for inviting me to come and to speak. I know a number of you here already, and it's nice to meet a number of new people at the same time. So the topic of my talk is acidification of water by CO2. We've heard from a number of people that the effects of carbon dioxide on temperature are going to be very modest, and okay. But one of the pushbacks on that is that the oceans will become acidic. And so oyster shells will dissolve and shrimp shells will dissolve. And of course, this is complete nonsense, but many people believe it. And so I want to tell you a few of the facts, so this will be a sort of a chemistry lesson this morning. And I apologize for that, but I know there are a number of good students here, so just out of curiosity, I looked at this is based on a paper that we have just posted by William Van Wijngaard and Peter Ridd from Australia. Wijngaard is from Canada. Marty Cornell and myself on acidification of water by CO2. And I just looked at the Google AI to see what it said, and even though it's only been out for a month, it said the acidification of water by CO2 argues that natural waters possess sufficient buffering capacity to negate risks from rising atmospheric CO2. Authors conclude that doubling CO2 causes minimum pH reduction within natural biological variations, challenging projections of significant acidification. Read the full preprint, so you can see the preprint address there. But the interesting thing is that 3 or 4 years ago, if you had asked Google something like this, it would immediately start ad hominems about, deniers, so things are changing for the better, I think, in terms of truth. So let's talk about ocean acidification. Even the community of ocean acidification alarmists is in deep trouble because none of the early experiments that were alarming have reproduced. So I remember 15 years ago, there were all of these experiments of dissolving oyster shells and, shrimps dissolving, and none of that has turned out to be true. And so this paper came out just a few years ago. It says reproducibility crisis and gravitation toward a consensus in ocean acidification research. I think the consensus, the honest is that most ocean acidification work in the past has been junk science. And I'll show you an example here. Here is a typical experiment that was done. Actually, this was done only a few years ago, in 2020, 5 years ago, 6 years ago. But the way oceans will be acidified by more carbon dioxide in the air is the air will put carbon dioxide into the oceans. The ocean will get a little bit more acidic. But that's a lot of trouble. So in the early days, people skipped that step and they simply added hydrochloric acid to the water or sulfuric acid. And that has a completely different effect on the water. If you add CO2 to ocean water, you increase the amount of carbon. It makes it easier for calcification to take place in an oyster or in a plankton. If you put hydrochloric acid into the water, you drive CO2 out of the ocean and into the air. So what people were attributing to ocean acidification, it was hurting the creatures in the ocean, but because there was less CO2 in the water, not because there was more CO2. CO2 for water creatures is a benefit just as it is for land plants. So let's talk about the effects of CO2. It's actually quite straightforward to calculate what happens if you change the amount of CO2 in the atmosphere. Indeed, the oceans will become a little more acidic, but the important point here is the little. It's a very small effect. So if you double CO2 from today is maybe 430 parts per million to 860, ocean pH will drop by about 0.25 units. That's a very small amount, from a little bit more than 8 to a little bit under 8 pH units. So PC is the current partial pressure of CO2, and PD is the double partial pressure. This depends on a lot of things. The most important one is salinity, so the effect of pH on fresh water is quite different from that on ocean water. And it depends a little bit on temperature. The temperature dependence is not very big. You can see we've plotted both 15 degrees and 25 degrees centigrade. There's not a great difference there. But this change in pH, 0.25, is quite small compared just to the day-to-night changes in the ocean. So here are some examples of what you actually observe in the ocean, and these are, on the left, I've shown some figures of measurements of pH. In the sterile open ocean, pH is indeed quite constant. It depends exactly where you are on Earth, but it's around 8. But if you go to productive regions where plants are growing, algae are growing, fish are abundant, pH varies by huge amounts just from day to night. So during the day, the pH level in the ocean rapidly increases. So the ocean is becoming less acidic during the day, and toward the end of the day, it may have increased by 0.2 pH units. And that's because the carbon dioxide in the water is sucked out of the water by the photosynthesizing organisms and converted into sugar and proteins, and so there's not enough CO2 left into the water to cancel the natural alkalinity of the ocean. The oceans, by the way, are extremely alkaline. Let me point out that if you took all of the CO2 out of the ocean, the pH of the ocean would be around 10 or 11 pH units, so that's about the same as drain cleaner. It's what you use to clean out your stopped-up drains. So the oceans are livable only because of the CO2 that's dissolved in it. The ocean is extremely alkaline, and without CO2, it would be unlivable for most creatures. So thank God for CO2. And if you, yes, one of many reasons to thank God for CO2, yeah. Anyway, these are direct measurements of pH in the oceans, and it's certainly not stable, and the amount that doubling CO2 will change the pH is less than the change from day to night to day. So it's clear that ocean creatures can handle that. It's not an issue. Here's another example. It's a cruise ship that started in Hawaii and cruised north to Alaska. But on the cruise, you start out with a very high pH, but that's because near Hawaii the sun is beating down, the water's quite salty, the alkalinity dominates the effects of CO2. As you move north to Alaska, the pH gets less and less. And also on this voyage, they drop probes down into the ocean beneath them and measure the pH at various kilometer depths beneath the ship. And the pH rapidly drops as you go down. The ocean becomes much more acidic at depth than it is at the surface. And again, that's biologically driven for the most part. The organic material that's produced in the sunlit layer of the ocean surface. When the plankton dies, the plankton sinks down under the force of gravity. It's heavier than water, so it sinks. And as it sinks, it's gradually oxidized, and the CO2 goes into the water, so the water becomes carbonated at lower depths. 2,000 or 3,000 meters, there's a lot more CO2 in the ocean than there is at the surface layers. So CO2 levels can drop by half a pH unit between the surface and the lower ocean. So again, this suggests that if you have evolved to live in the ocean, you're adapted to huge changes in pH. You wouldn't be there today if that weren't happening. I mentioned that seawater is actually quite alkaline. It's not that different from drain cleaner if you had no CO2. And this alkaline seawater sucks in CO2 from the atmosphere. So one of the tricks that we use in submarines is if you have an emergency, you typically have some alkaline CO2 getters in the submarines, and that will suck CO2 out of the air for a day or two and prevent it from rising to poisonous levels. And the ocean does much the same thing. It's extremely alkaline, so it's sucking CO2 in. So if you look at the concentration of carbon molecules dissolved into organic carbon in the ocean, it's 100 times greater than it is in fresh water, 100 times greater than it is in the atmosphere above, because of this alkaline chemistry of the ocean, which is sucking in CO2. So that ratio of carbon atoms in the water to carbon atoms in the air is called the Ostwald solubility, and it's quite large in the current oceans. And it slowly goes down as you add CO2 to the atmosphere, but it's not a large effect. That decrease is often quantified by something called the Ravel factor. So if there are oceanographers here, they will remember that. So what does CO2 look like in the water? There are actually three main species of CO2 in the water. When the CO2 molecules goes into water, most of the time it remains a CO2 molecule. It continues to vibrate. It has a very hard time rotating. So if you look at the infrared spectrum of CO2 dissolved in water, the rotational bands are gone. So the line narrows up because the water hinders the rotational motion, but the vibrational absorption is still there. But eventually the CO2 will attach a water molecule and become carbonic acid. That was the original name for CO2. If you read the literature of the early 1800s, they didn't talk about CO2, they talked about carbonic acid. And by carbonic acid, they mean this molecule that has two OHs on a carbon and on a carboxy, and that quickly loses its hydrogen ions and becomes either bicarbonate, or it can lose two hydrogen ions and become carbonate. So the ocean and most freshwaters are mostly bicarbonate CO2. It's not dissolved molecules of CO2, it's mostly bicarbonate, like a big factor. And this is what allows the oceans to suck in so much CO2, because the CO2 molecule that is dissolved in the water, instead of popping back into the atmosphere, gets converted to bicarbonate and carbonate, and then it no longer wants to go back into the air. And that's why the ocean absorbs so much carbon dioxide, because of the alkalinity of the water. And now, what is acidity? Acidity really means that when you consider self-ionization of water, water will break apart into a H plus ion and a hydroxyl ion, plus and minus parts. And that's called self-ionization. It was first studied by Arrhenius. It was the thing that led to the idea of ions dissolving in water. So it's an old idea, and it's true. And if there are equal numbers of minus and plus parts of the water, then that's neutral ocean. But that neutrality depends on many factors. They talk about it as a constant, but it's not constant at all. It depends on the temperature, it depends on the pressure of the water, it depends on the salinity of the water. So neutral pH, when there are equal numbers of H pluses and OH minuses, is quite variable in the ocean. Maybe I showed some examples of that back here. Here you can see the horizontal lines on this curve show neutral pH values. The value of 7 that you probably learned about when you were in school is only for pure fresh water at 25 degrees centigrade. Any other water, neutral pH is different, a different value. And you can see they vary by about a half a pH unit for typical natural waters. Okay, well, so how do you figure out what happens if you increase the amount of CO2 in the atmosphere? What happens to the acidity of water? And to do that, you have to remember that there are all sorts of reactions going on in the water at the same time. There's the self-ionization of the water breaking apart. There's the conversion of bicarbonate to carbonate. There's dissolution of any solid calcium carbonate in the water, for example, the shells of microorganisms or macroorganisms for that matter. And to calculate pH, you need to write down equations for all of these different components of the water and make sure that they're all satisfied simultaneously. And I mentioned that these equations are characterized by so-called constants. They're really not constants. You can't read this at all, but the biggest effect on these so-called constants is salinity. So, for example, if you look at how an oyster shell dissolved or a clam shell, it dissolves 100 times better in the ocean than it does in fresh water. So it's a huge effect from salinity. There is a lesser effect from temperature. It's not trivial, but it's a lot less than salinity. And there's even an effect of pressure. So if you go down in a submersible into the oceans, if you go the first kilometer down, you see that the mud is covered with white carbonate snow. You go further down, it's white carbonate snow. You get below perhaps 4 kilometers, all of a sudden there's no snow left. It's all gone, as though you had reached the snow line. And that's called a lysocline. So as the pressure of the ocean increases, the solubility of carbonate, of calcite, aragonite, the main crystals of calcium carbonate increases, and increases a lot. So below a certain depth, it's not possible for them to remain as solids. They all dissolve into the high pressure water of the deep ocean. It's driven by thermodynamics because it can minimize the volume if it dissolves. So that's well understood, and it's a large effect. So what's in the ocean? Well, typical oceans have around 35 grams of solids for every kilogram of seawater. For oceanography, you typically talk about moles per kilogram rather than moles per liter, and so I will do that. And if you look at that 35 grams of other components, the salinity, most of that is ordinary table salt, most of it's sodium and chlorine, but there are also many other ions there. There's quite a bit of sulfate, there's quite a bit of magnesium. We already mentioned the bicarbonate from the ocean, from the CO2 from the air, and calcium. It's a whole zoo, even uranium. You know, there's a lot of uranium in the oceans. In principle, you could mine it, but it is not economically sensible today. And that composition actually changes if you look at the geological record. For example, today the oceans have an unusually large amount of magnesium in them compared to calcium. And so many organisms that make shells in the ocean make them out of aragonite, which is a crystal form that forms when there's lots of magnesium in the ocean, rather than calcite. But if you go back 200 million years, you find that most of the organisms use calcite, not aragonite, and that's because 200 million years ago, there was a lot more calcium in the ocean and less magnesium in the ocean. So the oceans change over geological time. So what we have now are what are called aragonite seas, as opposed to the calcium seas back in the Permian. I mentioned at the beginning the importance of alkalinity. Many people don't understand that, but what the alkalinity is that if you, the simplest way to think about seawater is it's a combination of a strong base and strong acid. So, but the bases are slightly outweigh the acid. So the ocean is dominated by sodium hydroxide as opposed to hydrochloric acid. There's a little more sodium hydroxide. And that's what gives the natural alkalinity of the ocean. It's about 2.4 millimoles per kilogram. And all waters have alkalinity, with the exception of very pure water like rainwater, which has zero alkalinity. A little list of typical natural waters there. The alkalinities can get as high as 4,000 millimoles per liter in some of the saline lakes in East Africa, and it can be negative by nearly 1,000 in volcanic lakes, which have a lot of sulfuric acid, but more normal values are 2 or 3 millimoles per liter. Ocean is 2.4. Mississippi River is 2. So although the ocean is very, very salty, it still has almost the same alkalinity as the Mississippi River. Okay, so the basic calculation, I won't dwell on this, is that when you put together all of the things that are going on in the ocean, the reactions forward and reverse, you find a polynomial equation. And when I was a student, it was hard to solve even a quadratic equation. It was aggravating to have to solve this. But for the ocean, it's actually a fourth order equation if you include, say, boron, which is the second most important weak acid in the ocean. But with modern software, it's easy to solve that. So I'm so grateful. When I look back at my youth, I had to look at log tables to, do multiplications, and I don't have to do that anymore. Also, I can easily solve a high-order polynomial equation. So this makes it quite easy to calculate the alkalinity of the ocean. And here's a typical calculation. This is a busy plot, but on the bottom of this plot, I've shown partial pressure of CO2 in hypothetical atmospheres from almost nothing on the left to, several atmospheres, to 100 atmospheres on the right, And plotted on this, there are all these messy lines, but the most important one is the dotted black line. That's the dissolved inorganic carbon. So as you add more CO2 to the ocean, you get more and more dissolved. It's called DIC, dissolved inorganic carbon. And this pH changes rapidly. So for example, the red line is the concentration of H+, hydrogen ions, and that rapidly increases as you increase CO2. But the bottom line here is that almost nothing happens if you double CO2. I've shown here a dotted line. That's the current concentration of, the vertical dotted line is the current concentration of CO2 in the air. Doubling it almost makes no difference to the dissolved carbon. It increases a little bit and changes the alkalinity by a tiny amount, as we mentioned earlier, about 0.25, I would say. So there really is no issue there. People say, well, it's true that the pH doesn't change much, but the carbonate ion concentration will go way down, and that will make it impossible for shells to form because they need carbonate to combine with calcium ions or magnesium ions to make the shell, calcium mostly. But the oceans are actually supersaturated in calcite by a huge amount, by a factor of 5 or more. So the big question is, why isn't the ocean surface full of crystals of calcite? Because it's highly supersaturated. And the answer is that magnesium in the ocean suppresses the rate of formation. It's true that the ocean is heavily supersaturated, but the rates of formation of these crystals are extremely slow. So unless you have something in the ocean that has biological control, the formation of the crystals is too slow to matter. And so the oceans will remain heavily supersaturated in carbonate crystals, calcium carbonate crystals. If we double CO2, or even if you quadruple CO2, it won't make any difference. This plot here shows that the supersaturation is most pronounced at low latitudes near the tropics, but it remains supersaturated almost to the poles. Now, if you take the trouble to have a look at this paper and review the chemistry you might have learned at one time, you'll notice that it's almost all inorganic chemistry. There's no biology. We're following up that paper, especially with Peter Ridd from Australia, who's a real expert on the barrier reef, with some discussions of the biological aspects of ocean acidification. And that actually makes the whole picture even less threatening, because inside a coral polyp or inside an oyster or a clam, the external content of dissolved inorganic carbon almost doesn't matter. The interior of these organisms is under complete biological control, so they can pump in CO2 or they can pump out CO2. The energetic costs are trivial. And so, for example, you may know that most artificial pearls are grown in freshwater clams in China. And, the fresh water is heavily undersaturated. The pearls in the oysters should dissolve, but they don't dissolve at all, because the biological control of the clam is so effective that it doesn't matter that the outer waters are heavily subsaturated with calcium carbonate. So, for example, in a clam, this is a picture of what could be a clam, and none of the actual biomineralized parts, the calcium carbonate, are exposed to seawater. They're all exposed to internal fluids in the clam, where the pH and the calcium content, everything else is under very strict biological control. And so the same clam can grow a outer thick layer of calcite crystals to protect itself, and then underneath that there's often a nacreous layer. That's what pearls are made of, and that's aragonite. And they grow simultaneously, and they shouldn't do that if it was all inorganic chemistry, but it's not at all. It's all controlled by various biological molecules, quite very subtle. So I guess my conclusion here is that there really is no problem from CO2 acidification of the ocean. If you look into it, you can't figure out any way where this will make the slightest difference to the ocean. And we will follow up this paper with a secondary paper on some of the biology, and I hope you will take the trouble to look at it, if just to be able to push back against some of the nonsense that is peddled on ocean acidification. Of course, there's nonsense on every other issue with this topic. So thank you. I'll stop here.